Tutorial 6, Aircraft Systems. This lesson will cover aircraft systems. These include the engine, propeller, induction, ignition, as well as the fuel, lubrication, cooling, electrical, landing gear, and environmental control systems. An aircraft engine or power plant produces thrust to propel an aircraft. Reciprocating engines and turboprop engines work in combination with a propeller to produce thrust. Turbojet and turbofan engines produce thrust by increasing the velocity of air flowing through the engine. All of these power plants also drive the various systems that support the operation of an aircraft. Most small aircraft are designed with reciprocating engines. The name is derived from the back and forth or reciprocating movement of the pistons, which produces the mechanical energy necessary to accomplish work. Reciprocating engines operate on the basic principle of converting chemical energy, fuel, into mechanical energy. This conversion occurs within the cylinders of the engine through the process of combustion. The two primary reciprocating engine designs are the spark ignition and the compression ignition. Continued improvements in engine design led to the development of the horizontally opposed engine, which remains the most popular reciprocating engine used on smaller aircraft. These engines always have an even number of cylinders, since a cylinder on one side of the crankcase opposes a cylinder on the other side. The majority of these engines are air-cooled and usually are mounted in a horizontal position when installed on fixed-wing airplanes. Opposed-type engines have high power-to-weight ratios because they have a comparatively small, lightweight crankcase. In addition, the compact cylinder arrangement reduces the engine's frontal area and allows a streamlined installation that minimizes aerodynamic drag. Depending on the engine manufacturer, all of these arrangements can be designed to utilize spark or compression ignition and operate on either a 2- or 4-stroke cycle. Spark ignition 4-stroke engines remain the most common design used in general aviation today. The main parts of a spark ignition reciprocating engine include the cylinders, crankcase, and accessory housing. The intake exhaust valves, spark plugs, and pistons are located in the cylinders. The crankshaft and connecting rods are located in the crankcase. The magnetos are normally located on the engine accessory housing. In a 4-stroke engine, the conversion of chemical energy into mechanical energy occurs over a 4-stroke operating cycle. The intake, compression, power, and exhaust processes occur in 4 separate strokes of the piston. 1. The intake stroke begins as the piston starts its downward travel. When this happens, the intake valve opens and the fuel-air mixture is drawn into the cylinder. 2. The compression stroke begins when the intake valve closes and the piston starts moving back to the top of the cylinder. This phase of the cycle is used to obtain a much greater power output from the fuel-air mixture once it is ignited. 3. The power stroke begins when the fuel-air mixture is ignited. This causes a tremendous pressure increase in the cylinder and forces the piston downward away from the cylinder head, creating the power that turns the crankshaft. 4. The exhaust stroke is used to purge the cylinder of burned gases. It begins when the exhaust valve opens and the piston starts to move toward the cylinder head once again. Even when the engine is operated at a fairly low speed, the 4-stroke cycle takes place several hundred times each minute. In a 4-cylinder engine, each cylinder operates on a different stroke. Continuous rotation of a crankshaft is maintained by the precise timing of the power strokes in each cylinder. Continuous operation of the engine depends on the simultaneous function of auxiliary systems, including the induction, ignition, fuel, oil, cooling, and exhaust systems. The propeller is a rotating airfoil, subject to induced drag, stalls, and other aerodynamic principles that apply to any airfoil. It provides the necessary thrust to pull, or in some cases push, the aircraft through the air. The engine power is used to rotate the propeller, which in turn generates thrust very similar to the manner in which a wing produces lift. The amount of thrust produced depends on the shape of the airfoil, the angle of attack of the propeller blade, and the revolutions per minute, RPM, of the engine. The propeller itself is twisted so the blade angle changes from hub to tip. The greatest angle of incidence, or the highest pitch, is at the hub, while the smallest angle of incidence, or smallest pitch, is at the tip. The reason for the twist is to produce uniform lift from the hub to the tip. As the blade rotates, there is a difference in the actual speed of the various portions of the blade. The tip of the blade travels faster than the part near the hub, because the tip travels a greater distance than the hub in the same length of time. Small aircraft are equipped with either one of two types of propellers. One is the fixed pitch, and the other is the adjustable pitch. A propeller with fixed blade angles is a fixed pitch propeller. The pitch of this propeller is set by the manufacturer and cannot be changed. Since a fixed pitch propeller achieves the best efficiency only at a given combination of airspeed and RPM, the pitch setting is ideal for neither cruise nor climb. Thus, the aircraft suffers a bit in each performance category. The fixed pitch propeller is used when low weight, simplicity, and low cost are needed. There are two types of fixed pitch propellers, climb and cruise. Whether the aircraft has a climb or cruise propeller installed depends upon its intended use. The climb propeller has a lower pitch, therefore less drag. Less drag results in higher RPM and more horsepower capability, which increases performance during takeoffs and climbs, but decreases performance during cruising flight. The cruise propeller has a higher pitch, therefore more drag. More drag results in lower RPM and less horsepower capability, which decreases performance during takeoffs and climbs, but increases efficiency during cruising flight. The propeller is usually mounted on a shaft, which may be an extension of the engine crankshaft. In a fixed-pitch propeller, the tachometer is the indicator of engine power. A tachometer is calibrated in hundreds of RPM and gives a direct indication of the engine and propeller RPM. The instrument is color-coded, with a green arc denoting the maximum continuous operating RPM. Some tachometers have additional markings to reflect engine and/or propeller limitations. The RPM is regulated by the throttle, which controls the fuel airflow to the engine. Power output depends on air density. Air density decreases as altitude increases, and a decrease in air density, higher density altitude, decreases the power output of the engine. As altitude changes, the position of the throttle must be changed to maintain the same RPM. As altitude is increased, the throttle must be opened further to indicate the same RPM as at a lower altitude. A constant speed propeller is a controllable pitch propeller whose pitch is automatically varied in flight by a governor, maintaining constant RPM despite varying air loads. It is the most common type of adjustable pitch propeller. The main advantage of a constant speed propeller is that it converts a high percentage of brake horsepower into thrust horsepower over a wide range of RPM and airspeed combinations. A constant speed propeller is more efficient than other propellers because it allows selection of the most efficient engine RPM for the given conditions. An aircraft with a constant speed propeller has two controls, the throttle and the propeller control. The throttle controls power output, and the propeller control regulates engine RPM. This in turn regulates propeller RPM, which is registered on the tachometer. Once a specific RPM is selected, a governor automatically adjusts the propeller blade angle as necessary to maintain the selected RPM. On aircraft equipped with a constant speed propeller, power output is controlled by the throttle and indicated by a manifold pressure gauge. The gauge measures the absolute pressure of the fuel-air mixture inside the intake manifold and is more correctly a measure of manifold absolute pressure. At a constant RPM and altitude, The amount of power produced is directly related to the fuel airflow being delivered to the combustion chamber. As the throttle setting is increased, more fuel and air flows to the engine, and MAP increases. When the engine is not running, the manifold pressure gauge indicates ambient air pressure. The manifold pressure gauge is color-coded to indicate the engine's operating range. The face of the manifold pressure gauge contains a green arc to show the normal operating range and a red radial line to indicate the upper limit of manifold pressure. Induction systems. The induction system brings in air from the outside, mixes it with fuel, and delivers the fuel-air mixture to the cylinder where combustion occurs. Outside air enters the induction system through an intake port on the front of the engine cowling. This port normally contains an air filter that inhibits the entry of dust and other foreign objects. Since the filter may occasionally become clogged, an alternate source of air must be available. Usually, the alternate air comes from inside the engine cowling, where it bypasses a clogged air filter. Some alternate air sources function automatically, while others operate manually. Two types of induction systems are commonly used in small aircraft engines. One, the carburetor system, which mixes the fuel and air in the carburetor before this mixture enters the intake manifold. Two, the fuel injection system, which mixes the fuel and air immediately before entry into each cylinder or injects fuel directly into each cylinder. Carburetors are classified as either float type or pressure type. The float type of carburetor is probably the most common of all carburetor types. Pressure carburetors are usually not found on small aircraft. The basic difference between a float type and a pressure type carburetor is the delivery of fuel. The pressure type carburetor delivers fuel under pressure by a fuel pump. In the operation of the float type carburetor system, the outside air first flows through an air filter, usually located at an air intake in the front part of the engine cowling. This filtered air flows into the carburetor and through a venturi, a narrow throat in the carburetor. When the air flows through the venturi, a low pressure area is created, which forces the fuel to flow through a main fuel jet located at the throat. The fuel then flows into the airstream where it is mixed with the flowing air. The fuel-air mixture is then drawn through the intake manifold and into the combustion chambers where it is ignited. The float-type carburetor acquires its name from a float which rests on fuel within the float chamber. When the level of the fuel forces the float to rise, the needle valve closes the fuel opening and shuts off the fuel flow to the carburetor. The needle valve opens again when the engine requires additional fuel. The flow of the fuel-air mixture to the combustion chambers is regulated by the throttle valve, which is controlled by the throttle in the flight deck. The float-type carburetor has several distinct disadvantages. In the first place, imagine the effect that abrupt maneuvers have on the float action. In the second place, the fact that its fuel must be discharged at low pressure leads to incomplete vaporization and difficulty in discharging fuel into some types of supercharged systems. The chief disadvantage of the float carburetor, however, is its icing tendency. The drop in temperature due to fuel vaporization takes place within the venturi. As a result, ice readily forms in the venturi and on the throttle valve. Carburetors are normally calibrated at sea-level pressure, where the correct fuel-to-air mixture ratio is established with the mixture control set in the full rich position. However, as altitude increases, the density of air entering the carburetor decreases, while the density of the fuel remains the same. This creates a progressively richer mixture, which can result in engine roughness and an appreciable loss of power. The roughness normally is due to spark plug fouling from excessive carbon buildup on the plugs. Carbon buildup occurs because the rich mixture lowers the temperature inside the cylinder, inhibiting complete combustion of the fuel. This condition may occur during the pre-takeoff run-up at high elevation airports and during climbs or cruise flight at high altitudes. To maintain the correct fuel-air mixture, the mixture must be leaned using the mixture control. Leaning the mixture decreases fuel flow, which compensates for the decreased air density at high altitude. During a descent from high altitude, the mixture must be enriched, or it may become too lean. An overly lean mixture causes detonation, which may result in rough engine operation, overheating, and a loss of power. The best way to maintain the proper mixture is to monitor the engine temperature and enrich the mixture as needed. Proper mixture control and better fuel economy for fuel-injected engines can be achieved by use of an exhaust gas temperature gauge. Since the process of adjusting the mixture can vary from one aircraft to another, it is important to refer to the airplane flight manual or the pilot's operating handbook to determine the specific procedures for a given aircraft. As mentioned earlier, one disadvantage of the float-type carburetor is its icing tendency. Carburetor ice occurs due to the effect of fuel vaporization and the decrease in air pressure in the venturi, which causes a sharp temperature drop in the carburetor. If water vapor in the air condenses when the carburetor temperature is at or below freezing, ice may form on internal surfaces of the carburetor, including the throttle valve. The reduced air pressure, as well as the vaporization of fuel, contributes to the temperature decrease in the carburetor. Ice generally forms in the vicinity of the throttle valve and in the venturi throat. This restricts the flow of the fuel-air mixture and reduces power. If enough ice builds up, the engine may cease to operate. Carburetor ice is most likely to occur when temperatures are below 70 degrees Fahrenheit or 21 degrees Celsius, and the relative humidity is above 80%. Due to the sudden cooling that takes place in the carburetor, icing can occur even with temperatures as high as 100 degrees Fahrenheit and humidity as low as 50%. This temperature drop can be as much as 60 to 70 degrees Fahrenheit. The first indication of carburetor icing in an aircraft with a fixed-pitch propeller is a decrease in engine RPM, which may be followed by engine roughness. In an aircraft with a constant-speed propeller, carburetor icing is usually indicated by a decrease in manifold pressure, but no reduction in RPM. Propeller pitch is automatically adjusted to compensate for loss of power. Thus, a constant RPM is maintained. Although carburetor ice can occur during any phase of flight, it is particularly dangerous when using reduced power during a descent. Under certain conditions, carburetor ice could build unnoticed until power is added. To combat the effects of carburetor ice, engines with float-type carburetors employ a carburetor heat system. Carburetor heat is an anti-icing system that preheats the air before it reaches the carburetor and is intended to keep the fuel-air mixture above the freezing temperature to prevent the formation of carburetor ice. Carburetor heat can be used to melt ice that has already formed in the carburetor if the accumulation is not too great, but using carburetor heat as a preventive measure is the better option. Additionally, the use of carburetor heat as an alternate air source can be used if the intake filter clogs, such as in sudden or unexpected airframe icing conditions. The carburetor heat should be checked during the engine run-up. The use of carburetor heat causes a decrease in engine power, sometimes up to 15%, because the heated air is less dense than the outside air that had been entering the engine. This enriches the mixture. When ice is present in an aircraft with a fixed-pitch propeller and carburetor heat is being used, there is a decrease in RPM, followed by a gradual increase in RPM as the ice melts. The engine also should run more smoothly after the ice has been removed. If ice is not present, the RPM will decrease and then remain constant. When carburetor heat is used on an aircraft with a constant speed propeller and ice is present, a decrease in the manifold pressure will be noticed, followed by a gradual increase. If carburetor icing is not present, the gradual increase in manifold pressure will not be apparent until the carburetor heat is turned off. In a fuel injection system, the fuel is injected directly into the cylinders or just ahead of the intake valve. The air intake for the fuel injection system is similar to that used in a carburetor system, with an alternate air source located within the engine cowling. A fuel injection system usually incorporates 6 basic components: an engine-driven fuel pump, a fuel air control unit, fuel manifold, fuel distributor, discharge nozzles, an auxiliary fuel pump, and fuel pressure flow indicators. The auxiliary fuel pump provides fuel under pressure to the fuel air control unit for engine starting and/or emergency use. After starting, the engine-driven fuel pump provides fuel under pressure from the fuel tank to the fuel air control unit. This control unit, which essentially replaces the carburetor, meters fuel based on the mixture control setting and sends it to the fuel manifold valve at a rate controlled by the throttle. After reaching the fuel manifold valve, the fuel is distributed to the individual fuel discharge nozzles. The discharge nozzles, which are located in each cylinder head, inject the fuel-air mixture directly into each cylinder intake port. A fuel injection system is considered to be less susceptible to icing than the carburetor system, but impact icing on the air intake is a possibility in either system. Impact icing occurs when ice forms on the exterior of the aircraft and blocks openings such as the air intake for the injection system. Advantages of fuel injection: reduction in evaporative icing, better fuel flow, faster throttle response, precise control of mixture, better fuel distribution, and easier cold weather starts. Disadvantages: difficulty in starting a hot engine, vapor locks during ground operations on hot days, problems associated with restarting an engine that quits because of fuel starvation. Please help us spread the word about Pilot Training System, and we look forward to further servicing your flight training needs.